All right, so we are going to talk about continuous probability distributions today. So realize up until now we have talked about discrete probability distributions other than just introducing the difference between continuous and discrete data that we talked about in chapter 1. But everything we've done so far, when we've looked at frequency tables and created histograms, and we looked at the binomial distribution and the geometric distribution, those are all discrete distributions, finite number of outcomes. When we found the mean and standard deviation of discrete probability distributions, putting the lists in our calculators, doing all of that fun stuff, that was all discrete probability distributions. We are now going to move to continuous probability distributions. So the big leap when we talk about continuous probability distributions are, and I think I prepared you for this earlier, talking about that eventually in this class we were going to start measuring probabilities as areas under a curve. And that's where we're going now. And when we do this, because there is no area under a single value, right? Probability of any single value in a continuous probability distribution is going to be 0. That's because there's no area underneath a single value. If we look at, this is kind of, we're going to introduce continuous probability distributions using a special continuous probability distribution called the uniform distribution. The uniform distribution means that all the outcomes are equally likely. And that's why we get a straight line here when we look at a probability distribution called a uniform distribution. And notice if we take the value under one single value, let's say whatever this is here, C, we'll call it C, there is no area under one single value. So for a continuous probability distribution, we can only find values between two values, greater than a certain value, less than a certain value, but not the probability of any single value. Now, this also leads us to the realization that if we use less than or equal to, it doesn't matter to us. If we use greater than or equal to, same thing, doesn't matter to us here. So for a continuous probability distribution, less than or equal doesn't make any difference to us. Similarly, for greater than and greater than or equal to. All right, and the total area underneath the curve is always going to be 1 because, again, that's the sample space, right? We talked about sample spaces. The sum always has to equal 1. Well, here the total probability is the area underneath the curve. Even though this is a rectangle, we're going to call it a curve. The total area under any probability distribution must equal 1. So in this case, in a uniform distribution, we're going to have some endpoints between A and B, and we're going to have a height. Shouldn't put that there yet, I haven't calculated it yet. But we have a height and a width. In this case, I'm starting with the uniform because it's kind of the simplest area to deal with, the area of a rectangle. Hopefully we all realize the area of a rectangle is length times width. So pretty easy here. Let's look at a theoretical distribution. Okay, so let's say we're going to look at the time you wait for a cup of coffee at Starbucks. Okay, and let's say that the sample space is between 5 and 20 minutes. Okay, so we're going to say all the outcomes are equally likely so that we can use a uniform distribution. It's a continuous distribution. The low point is 5, the high point is 20. So if we put that here, let's say this would represent that distribution. Low end of 5, high end of 20. We're talking minutes here on the x-axis. So we got to come up with the height. Well, we know the total area has to equal 1. Right? So this is going to allow us to determine the height. Okay. So the height is length times width. So the length here is the difference between the two endpoints, 20 and 5. And the height is what we're looking for, and we know that area equals 1. So width times height equals 1. That leads us to the height, solving this equation, 1 over b minus a. And in this case, that's 1 over 15. Right? So 1 over 15 is going to give us the shape of this curve. So 1 over 15 is the height, 20 and 5 are the endpoints. Length times height is going to give us the area of 1. We call the curve itself, if we were to put this into our calculator and draw it, we call that the probability density function. The probability density function is the shape of the curve. Again, it's not always going to be a straight line, but it's the shape of the curve that's going to give us our area to calculate probabilities. The uniform distribution, first we'll look at something called the random variable that we're asking about. When you see a large X, letter X, that's called a random variable, and that's going to take on any value in the interval of, in this case, this sample space 5 to 20 minutes. And we're saying it's a uniform distribution. So this will be represented like this. I want you to get used to this notation here. Read this as the random variable X is distributed. This little squiggly line here means this random variable has a distribution that is uniform with these endpoints. Okay, so if you see this, this is describing this probability density function, which you come up with by using the endpoints that are given and finding the height, which gives you that curve or density function, which we're going to use to find probabilities. And we're given that this random variable ranges from 5 to 20. So just notation, how to come up with the curve when it's a uniform distribution. Uniform distribution is continuous in this case. So we're going to ask questions like this. What's the probability that your wait time is greater than 9 minutes? What's the probability that your wait time is less than 18 minutes? What's the probability that your wait time is between 9 and 18 minutes? So questions like that. These are the questions we want to be able to ask. So let's answer those questions. What's the probability that your wait time is going to be greater than 9 minutes? Again, we don't care. Greater than, or equal to does not make a difference for us. So this is pretty simple stuff, people. I mean, all we got to do is find the area under the curve between 9 and 20, right? Between 9 and the endpoint of 20. Well, yeah, we know how to find the area of a rectangle, length times width, or base times height, we'll call it. The base, if we go between 9 and 20, so let's say we got 9 here, somewhere, let's call this 9, and 20. So we're just looking for the area under the curve between 9 and 20. Pretty easy, right? Area under the curve between 9 and 20. Well, it's a rectangle. Base times height. That's all we're doing. Base times height. Base is 11. Height is 1 over 15. We get our answer of 11 over 15. 11 over 15. Right here. What's the probability that your wait time is less than 18 minutes? Same idea. Base times height. There's our probability, 13 out of 15. Probability that X is between 9 and 18. Base times height gives us our answer. Right? So just the area under the curve between two values, greater than one value, less than one value. That's all we're doing here. We can also ask questions such as, what is the 80th percentile? So you want to be able to answer questions like this. Find the 80th percentile. Well, this is the same logic. It's just kind of looking at it from a different angle. Okay? So we're looking for some C value. We're looking for some C value such that the area less than C is 80%. Right? The C value here to be the 80th percentile, to be the 80th percentile here, the area between 5 and C has to be 80%. So we just use the same idea and calculate those numbers. We're looking for the C such that the probability that X is less than C is 80%. Now that nicely translates into 15ths. It's not always, but it doesn't matter. In this case, it just makes it a little easier to see what's going to happen here. So we need, again, the probability we know is the base times the height. The base here is C minus 5. Right? We look at the base. The base here is going to be this distance here, C minus 5. That's the base. The height is always 1 over 15, and we need that to equal 12 over 15. So again, pretty simple calculation. Base, C minus 5. Height, 1 over 15. We need that to equal 80%, or 12 over 15. We're just solving this one variable equation. We're all very good at solving one variable equations because we're all excellent algebra students. So we multiply both sides by 15 from this equation to this one. Nicely, 15 over 15 just reduces that product down to 12. And then we add 5 to this 12 to get our C value of 17. So 17 is the 80th percentile. Right? Between 5 and C, 80% of the probability. We calculate that and see that our C value is 17. And with this example, it's again pretty easy to see. There's 3 here. This would be the width, 3 over 15. That's 1/5. 4/5 is 80%. So it all comes together nicely. Now we also want to be able to find the mean and standard deviation of a uniform distribution. And we have very nice formulas for these things. The mean for a uniform distribution, we're using the uniform distribution to introduce ourselves to continuous distributions. The mean of a uniform distribution is just the sum of the endpoints over 2. So we get 12.5 here. Standard deviation has this formula. Again, all you need is the A and the B. You plug in the A and the B, you calculate, and you get the standard deviation there of this particular distribution of waiting times for coffee at Starbucks between 5 and 20 minutes. So a continuous probability distribution. We're now looking at area under a probability density function to find the probabilities. And one more thing here. You might see a conditional question such as this, dealing with these distributions. Let's say you're asked this question: what's the probability that your waiting time is greater than 9 minutes, given that your waiting time is already greater than 6 minutes? So when you're asked this sort of conditional question, what it does is it changes the sample space, because the given condition here is greater than 6. Okay, so now the sample space, instead of being from 5 to 20, the sample space has shrunk to from 6 to 20. So that's kind of the main thing here. Given this condition, your sample space has changed, and it's restricted to just greater than 6, because the condition is that you've waited 6 minutes. And once you do that, now you're just looking at the same idea, except your density function is changed, because now your width here has changed. Now this is the sample space, and that's a width of 14. So now your height is going to be 1 over 14. And you're going to use that as your density function. This is your new situation. Given your waiting time is greater than 6, what's the probability that it's greater than 9? So now you're just finding this area under this density function. What's the probability that X is greater than 9? The base is 11. The height now is 1 over 14. So your answer is 11 over 14. Now, if we go back to the original distribution, Okay, so here's a picture of where the height is 1/14 in the restricted sample space. If we go back to the original definition of conditional, we can use that too. I just want to show you that you'll get the same answer. This is, I think, the easier way to look at it. But if you remember your conditional formula, probability of A given B, probability of the intersection over the probability of the condition, and we name our events A and B as greater than 9 minutes on the condition that it's greater than 6 minutes. If we use this formula and look at our original distribution, probability of A given B, probability of A and B, so greater than 6 and greater than 9, well, that's just this portion here. This is the only points that are both greater than 6 and greater than 9. So that's 11/15. And then you divide out the condition of greater than 6. Greater than 6 is going to be 14/15. We invert and multiply, and we see we get the same answers. All right, so good times there. Continuous probability distributions. See you next time.